All right, everybody, let's get back into chapter 8. So we're going to be looking at the localized electron bonding model. So this is going to be something we really want to make sure we understand. This is kind of a core part of learning about bonding. So when we talk about bonding, we're talking about the sharing of electrons. And so in molecules, what they're going to do is they're going to have electrons in their specific orbitals. Orbitals are going to have to end up lining their phases up. So they're going to let's see, they're going to have to line their phases up. So you can't have two orbitals form a molecular orbital when you have different phases hitting each other. So if you look to the left, you see how the different phases are going to be your blue and your blue and your burgundy there. And so I can't have a blue and a burgundy atomic orbitals come together to form a molecular orbital. So you're going to have spatial orientation down. You're also going to have orbitals at nearly the same energy, if not exactly the same energy. So these are just some constraints on actually forming bonds inside of molecules. Now, we're not going to go deep into all of that because that would involve high-level quantum chemistry. But what we are going to do is we're going to start looking at what's known as Lewis structures, which you see there at the bottom, where we're going to be placing electrons in molecules as we bring the atoms of the molecule together. And we know that what's going to be happening is we're going to be going from the individual electron placements of an atom to brand new electron placements in the molecule. So going from and if we look at these as orbitals, that would be going from atomic orbitals to molecular orbitals. So we're going to be looking at different types of electrons. We have bonding electrons and lone pairs. Everywhere you see a straight line, that's going to be a bond. And in that bond are going to be electrons. So every line that you see is worth 2 electrons. So if you see a double bond, if you look here, you see 1, 2. It's 2 lines. Each one of those is 2 electrons. So that's a total of 4 electrons. We want to make sure we're getting that down where that single bond between hydrogen and carbon, that's 2 electrons. And then lone pairs. Lone pairs are going to be electrons that are centralized on a specific atom that are not going to be involved in the bonding process. Okay, Lewis structures. Lewis structures are going to be simple dot structures uh, that are going to place valence electrons in their proper positions. We have them for both atoms and molecules. So when we're talking about Lewis structures for atoms representing valence electrons, well, all Lewis structures representing valence electrons, we can start by looking at the electron configuration of an atom. But then what you want to do is relate these structures and the number of valence electrons to the periodic table. So if we go through, group 1 gets 1 valence electron, group 2 gets 2 valence electrons. We're going to jump over and we're doing main group elements. So 3 valence, 4 valence, 5 valence, 6 valence, 7, and 8. So you want to be able to link the number of valence electrons to the group that the atom is in. So let's look at sodium, for example. Sodium's electron configuration. So you see that the valence for sodium is in the n equals 3 level. That's the highest value for n. And so that's going to be your valence electron. And there's the 1 electron. So our Lewis dot structure for sodium is going to be that, where we just put the 1 dot on there to represent the 1 valence electron. And then every atom in column 1 will have the same kind of dot structure. What about calcium? So here is a group 2 element for this one. We have argon, 4s2. Those two electrons in the 4s2 level, those are the valence electrons. And so we need a structure, a Lewis symbol that will represent this. Now, where I place the dots, this is how I was taught to do it. I think this is the most traditional way, but as long as you're not over-representing valence electrons, I don't think people are super picky about it. Let's go to boron. This is a group 13 or 3A. Boron's right there. And so this one's going to have three valence electrons. Let's figure that out. So this is helium, 2s2, 2p1. There are the three valence. So that means boron is going to have a Lewis structure like that. And we can keep going through carbon. That's going to be four valence. Now we're getting into something where you want to break down your atoms into kind of a square. And so you're going to have four sides. You really want to set up a Lewis structure for your atoms where every side gets at least one dot. I wouldn't want to do carbon like that. So make sure you're getting at least one dot in each of the four locations, and then go back and start pairing. So let's see, nitrogen, that's five valence electrons, because again, nitrogen's right there. That means oxygen will be six, fluorine will be seven, and then neon will be eight. So nitrogen, let's do one, two, three, four, and then five. Okay. What about fluorine? No, hang on. Oxygen. Oxygen is six. So we'll do one, two, three, four, five, six. We'll do fluorine with seven valence. One, two, three, four, five, six, seven. Now you don't, when you draw them, you don't really have to go around in a circle, like circles like that, but just make sure every side is getting at least one electron. And then neon. Neon's a noble gas. It has eight valence electrons. Remember, it has that filled valence shell, so it's very stable. So there'd be your Lewis symbol for neon. So what you're going to be seeing is we're going to be using general rules as we go through and work with Lewis structures, but these rules are not absolute. There's always exceptions to the rules. And so we're going to be dealing with Lewis structures in VSEPR. So VSEPR is valence shell electron pair repulsion. And what that's going to do is that's going to create molecular geometries where your groups of electrons are going to want to get as far away from each other as possible. So, like for example, we talked about noble gases having that filled valence shell. Here you can see argon. I've highlighted the valence shell. That should be stable. And so for the most part, noble gases don't form bonds with other atoms. But that's not always true. You're going to see in one of the exercises, xenon is fairly well known for forming bonds. So there's not these hard and fast, so the rules are not absolute. Also, make sure you're taking note of the fact that not all valence shells are going to have eight electrons. So you see there helium. If you think about the periodic table, helium's electron structure is 1s2. That means it only goes out to the energy subshell of 1s. And so if you think about that, the n equals 1 level can't go beyond s. The s subshell, which we talked about in quantum numbers, can't have more than one orbital. So since helium has a maximum of one orbital on it, that means it maxes out at two electrons. So we're going to be talking about several rules. Your overarching rule is going to be the octet rule. However, we have some things that happen with the first few atoms on the periodic table. And at least up through kind of up through beryllium, there's even going to be exceptions there. You're going to get what's called the Duet rule, where two electrons in the valence shell make a very stable molecule, very stable bond. So, for example, let's look at H2. So each H atom is going to have a Lewis structure like that. And when I make H2, now the way I start building Lewis structures is I'm going to put down my atoms. I'm going to draw a single bond between them. And then I'm going to look to see, are there any electrons on my atomic Lewis symbols that I didn't use? In this case, no. And so your hydrogen molecule is this homonuclear diatomic with a single bond, but you notice here there's only one bond, so that's two electrons. But this is completely stable for hydrogen because each hydrogen only has a 1s shell to work, a 1s subshell to work with. So that's a maximum of two electrons. So your hydrogen is going to follow your Duet rule. Let's look at lithium hydride. This one's going to be covalent because both lithium and hydrogen are nonmetals. Lithium is in group 1, so it has that Lewis symbol. Hydrogen is in group 1, it has that Lewis symbol. So again, you're going to get a Lewis structure where each atom only gets two electrons because both atoms are going to get the two electrons in the bond. So when you're looking at Lewis structures and you're counting, uh, each atom will count the electrons in the bonds. But let's look at beryllium when it's in an ionic compound. So we know that beryllium is group 2, so we're going to have that and that. Oxygen is in group 6. 1, 2, 3, 4, 5, 6. But oxygen is also very electronegative. So it's going to steal these electrons. And that's going to leave us with beryllium and oxygen. So we have this +2 -2 ionic compound. And you see these two electrons right here are going to give beryllium that Duet rule. But there are exceptions to this. So, and we'll talk about this again later, when beryllium, for example, is in an ionic compound, it follows a Duet rule. When it's in a covalent compound, it does not. So what if we have beryllium dihydride? Well, our Lewis symbol for beryllium is going to be 2 electrons. Hydrogen is 1 electron. Beryllium is going to be our central atom. And so then one thing you want to look at, everywhere you see a single electron, you want to think of those as bonding locations. So I need 2 hydrogens attached to this. I'm going to make my single bonds, put hydrogen, and then I'm going to say, are there any electrons that I did not use in the bonding? So each hydrogen, we'll go ahead and put another one there. So each hydrogen used its one bonding location, so there's no electrons left. Beryllium has 2 bonds, so it used its 2 bonding locations and there's no electrons left. So this is the Lewis structure for beryllium hydride. We don't need to put any other electrons anywhere. Beryllium dihydride, it's covalent. And so here you see the beryllium has 4 electrons around it. Now, since beryllium has become covalent, you're going to see in a little bit, this is it now, instead of following the Duet rule, it becomes an atom that breaks the octet rule by being electron deficient. And so we'll do that a little bit more here in a few minutes. Another interesting molecule is beryllium difluoride. And so again, this is going to be, this one may look like it's going to be ionic. This one's going to actually end up being covalent. I'm going to explain this to you, and I want you to follow along as best you can. So your beryllium is going to start like this. We're going to get our symbols here. It's going to have two fluorines. So fluorine has 7 valence. I'm going to go ahead and put those on either side because beryllium is our central atom. So we know fluorine's highly electronegative. So we usually think of the fluorines as stealing electrons, where that's going to leave us with a negative fluorine. Beryllium had 2 electrons stolen, so it's positive. And that's negative. And now, I mean, this makes sense to us. And then, of course, you would have the electrostatic attraction. But what ends up happening is as these atoms come together, the beryllium actually has enough strength to pull electrons back toward itself to create covalent bonds, albeit they're very, very polar, but they're still covalent. And that's because of something called Fagen's rule. And so the way you think about it is, you remember when we were talking about ionic radius, beryllium has a very, very small ionic radius. So let's look at this in a way that helps us understand charge density. And so if you have atom X and it's this size and it's +2, and you have atom Y or ion Y and it's this size and it's +2. What you have to ask yourself, which one of those would be more dense with its charge? Okay, so that'd be atom X. So that tiny one has the same amount of charge in a much smaller space. That means its charge is very, very dense. And so that's what happens with beryllium. And so that charge density is so strong that what it does is it ends up pulling electrons off of the electronegative fluorines just enough to create covalent bonds, and that's Fagen's rule. So the more dense the charge on a positive ion, the more likely it is to actually create covalent bonds where you wouldn't expect it. But what we want to notice here is that again, beryllium, yep, has 4 electrons around it. And so this again is not going to be following the Duet rule. It will be following it'll be an electron deficient molecule where it was trying to reach the octet rule. So again, some of these atoms, they follow the Duet rule only when they're in ionic form, like beryllium. Boron has kind of its own rule. It exists in a space where 6 valence electrons are good for it. So let's take, and again, remember, all of this is to create a stable molecule. All of this is to create stable molecules at the lowest energy possible. So boron has 3 valence electrons. Chlorine has 7. Okay, so what I'm going to do, I'm going to put my boron in the middle. I'm going to bond 3 chlorines. And so I see that boron uses all 3 of its bonding locations. Each chlorine uses its 1 bonding location. And then I have lone pairs that I now have to replace on the chlorine atom, the chlorine atoms. And so you can see here, these are the electrons that were not used in bonding, so I replaced them. And now you look, each one of these is 2 electrons. So boron is pulling in 6 electrons around itself. It's still electron deficient. It does not meet the octet rule, but it's very stable and very happy there. Now, once you get to carbon and beyond, the atoms in your molecules are going to want to reach the octet rule. So hydrogen won't, boron rarely will, your lithium and beryllium will not, but carbon and beyond, they're going to want to reach that octet rule. And so that is going to be 8 valence electrons around an atom. And when you're making your Lewis structures, the more atoms you can get in the octet rule, the better off you're going to be. So let's look at methane, CH4. So carbon has 4 valence. Hydrogen has 1 valence electron. So carbon's going to be center. I need to bond 4 hydrogens to it. Then I'd say, are there any electrons to replace? So carbon used all 4 of its bonding locations. Each hydrogen used its 1 bonding location. So no, this is going to be our Lewis structure for methane. What about something like CH2O? This is a good one to work with. Formaldehyde. We all know that smell. We've all taken the high school class where the teacher opens up the jar and you get that really horrible smell that comes out. That's formaldehyde. So what do we have here? We have carbon, which has 4 valence. Each hydrogen will have 1 valence. And then your oxygens, 2, 3, 4, 5, 6 valence. So carbon is going to be central here. And how do you pick the central atom? Well, a lot of the time it's going to be the atom that is the lowest in number. Sometimes there's not a central atom. A lot of this is going to take practice, and you'll get used to figuring out which atom is which. So carbon is going to be central. I need to bond 2 hydrogens and an oxygen to it. So 1, 2, 3. Hydrogen, hydrogen, oxygen. Now let's look at what electrons were used. So carbon used that location, that location, that location. Each hydrogen used its location. And so far, the oxygen has used one of its locations. Now I'm going to replace the electrons that were not used. So there's the 1 on carbon. Oxygen, you're going to have your 1, 2, 3, 4, 5. Your book does this a little bit differently. I don't care which method you use. But then we say, oh, so what can happen here? Because if you notice, carbon has 2, 4, 6, 7 electrons around it. So it does not meet the octet rule. It's not happy. Oxygen has 2, 4, 6, 7. It also does not meet the octet. What can I change for these both to reach the octet? Well, this electron can come in here. This electron can come in here. And what we get is a double bond. Now, yeah, I'm changing the shape a little bit here. I'm doing this according to Vesper. Remember, your electrons are going to want to get as far away from each other as possible, so that includes electrons in bonds. And now I replace the electrons that weren't used, and that's the 2 lone pairs on oxygen. Now, if you count, every atom will have an octet, except for hydrogen will have its 2 electrons where it's happy. Let's look at carbon monoxide. Okay, so there's no central atom. So carbon needs to bond to oxygen. What's used? I used that location on oxygen, and I used one of the locations on carbon. Okay, so now let's replace what wasn't used. So oxygen is going to get its 2 lone pairs, and then the 1 electron that wasn't used, carbon, is going to get 1, 2, 3. And so carbon has 1, 2, 3, 4, 5 electrons around it. Oxygen has 1, 2, 3, 4, 5, 6, 7 electrons around it. So what's the first thing we can do? Okay, well, let's push in an electron, push in an electron. This is going to give us carbon, double bond. Now, what we're going to do is these two electrons on carbon, we're going to bring those together. Then oxygen has 1, 2, 3, 4. It's lone pairs left over. Okay, so oxygen has 2, 4. Oxygen has 8. It's happy. Carbon has 6. So 2, hang on. Each bond, remember, 2 electrons, 2 electrons, 2 electrons. So carbon only has 6 electrons. It's not happy. So now what can happen? Well, one of these electron pairs from oxygen can swing in here, and we can get carbon, triple bond, oxygen, and we didn't touch that lone pair, and there's still a lone pair left on oxygen. And now each one of them has an octet, so this molecule's happy. Let's keep going. What about CO2? Carbon, whoopsies. Each oxygen is going to have 6. 1, 2, 3, 4, 5, 6. Okay, so carbon's going to be central. We need to bond 2 oxygens to it. And so what was used, that and that was used. Each carbon used one of its bonding locations. Let's replace what wasn't used. So I'm going to do bonding location. Carbon has its 2, and then 1, 2, 3, 4. Now, just to make this cleaner, I'm going to go ahead and put the 1, 2, 3, 4 on that oxygen, and then its unused bonding location. And I hope you can see that, so right now carbon has 2, 4 electrons from each bond. So 2 electrons from each bond is a total of 4. And then those last 2 electrons, that's 6. So carbon has 6. Each oxygen has 2, 4, 6, 7. So no one's happy yet. But if I take these electrons and put those in there, and these electrons and put those in there, what I'm going to get is each oxygen is going to be connected by a double bond. I did not touch its lone pairs. I've used all the electrons on carbon. And if you look now, everything has 8 electrons, so this is a happy molecule. Let's work with H2O. Hydrogen has 1 valence, oxygens have 6. I need to, let's see. Yeah, we'll do Vesper later, but I need to put my oxygen in the middle, bond 2 hydrogens to it. Okay, so each hydrogen uses its location. Oxygen has used both of its locations. And then I replace the oxygen lone pairs I didn't use. And that's actually the Lewis structure, because if you look, hydrogen has its 2, where it's happy. Oxygen has an octet. Now, of course, later on when we're doing Vesper, your water actually is going to look like that. But for now, we're just worried about simple Lewis structures. Let's try a few more. Let's look at N2. Each nitrogen has 5 valence. There's no central atom. Just need to bond nitrogen to nitrogen, and each one of them only used one of its bonding locations. That means we need to replace lone pair, and then 1, 2, 1, 2. So we want to get this to the point where nitrogens have an octet. So what can I do? I can say, well, these 2 here can come in, form a bond. These 2 here can come in and form a bond. And so then I'm going to get nitrogen, triple bond, with the lone pairs on the outside, and each nitrogen now has an octet. Let's work with, let's do the cyanide ion. And we'll think about where, because you see it's a -1. So an extra electron has to come from somewhere. Look at our atoms. All right, so if I bond carbon to nitrogen, I've used that one, I've used that one. Let's replace what I didn't use. Okay, so lone pair on the nitrogen and 2 single electrons, then 3 single electrons on the carbon. Now, the way I can get at least nitrogen to octet, 2, 4, 5, 6. So I'm going to go like this because I'm trying to also maximize electrons on the carbon. And what do I have? I have an octet on nitrogen, but carbon only has 7 electrons. This is where the extra electron comes in. So carbon has a space for an electron. It's going to come in there. So then we're going to get, and I'm going to put this structure inside of brackets because when you have an ion, oops, you want to put its structure inside of brackets. And then I put the negative charge. So there is how we create an ion. We start by making our Lewis structure and then say, okay, well, where do we need to fill in? And that's where that extra electron went. Let's do C2H4. Each carbon will have its 4 valence. Hydrogens will have 1. Okay, this one, there's no central atom, so let's do carbon bonded to carbon. And then each one of these is going to get a hydrogen because we want to try to balance out the hydrogens across the molecule. And so then each carbon used 1, 2, 3. Each hydrogen used its 1. That means each carbon has an electron left over. And to get to octet, we can take these electrons and move them in. And this is going to give us C, double bond to C. So really your Lewis structures are just going to take a little bit of practice. And you'll get to the point where you can do these pretty flawlessly. Here's an exercise. Maybe, pause the recording and see if you can get these. So let's look at O2. Each oxygen is going to have 6 valence. So if I bond oxygen to oxygen, each one of them is going to use one of its bonding locations. So now I'm going to replace what I didn't use. Okay, now what I can do is take this and push those in there. And what I'm going to get is a structure where oxygen, each one of them has an octet. Now, that's your standard Lewis structure for oxygen, but it doesn't tell you the whole picture. This is what I mean by there's exceptions to rules. We have processes and constructs that we use to explain what's going on, but they don't always give the full picture. Now, if you're in one of our biology classes, you're going to be asked about, okay, well, if this is the case and all of our electrons are paired, why is oxygen susceptible to a magnetic field? Okay, well, in reality, and you would learn this way down the road, what you get with oxygen is you're going to get these two lone electrons that are then going to form partial bonds across with those lone pairs. With lone pairs, you're going to get, and these single electrons both spinning in the same direction gives a positive angular momentum, which makes oxygen magnetic. But if I have two partial bonds, well, and I have one bond in the middle, that's going to give me a total of two bonds. So as you go through chemistry and you get further along, you're going to learn a lot more of this at a deeper level. It's just right now we're using the constructs that we can use to explain what's happening in a molecule without having to do the in-depth quantum mechanics. So what about HCN? Okay, well, this one's kind of like the cyanide we just did, except we don't need the extra electron. One valence for hydrogen, four for carbon, five for nitrogen. Okay, so carbon's going to be central. And again, this takes practice. It's going to be bonded to nitrogen, bonded to hydrogen. And again, you can look at it and say, well, carbon has the most bonding locations. Nitrogen is going to have a lone pair on it. So more than likely, carbon is going to be your central atom because it can take on more bonds. Okay, but let's let's look at what was used. So hydrogen used that, carbon used those, nitrogen used that. So let's replace what wasn't used. Okay, so we have here and here, the lone pair on nitrogen, and then it's single electrons. Okay, now if I take and I move these in here, you'll see I end up with a structure where hydrogen has its two, carbon has eight, so two per bond, four bonds, that's eight, and nitrogen has its eight. So this, everything has a filled valence shell, and carbon and nitrogen meet the octet, so that's a good molecule. And then our last one is NH3 or ammonia. Nitrogens have five. Each hydrogen only has one valence. So let's go ahead and put nitrogen in the center. And then we're going to bond three hydrogens to it. And so let's see, nitrogen used its three single bonding locations. Each hydrogen used its one. Nitrogen then has a lone pair left, and then that turns out, so then that's your actual completed Lewis structure. Because again, each hydrogen has its two, nitrogen has eight. Now we'll talk a little bit about exceptions to the octet rule. We've already talked about boron. So there, you see that boron is electron deficient. Beryllium is electron deficient. So boron, as you notice, it has two, two, and two. That's six electrons, so it doesn't reach the octet, so it's electron deficient. Your beryllium has two and two, so that has four electrons around it, making it electron deficient. Remember, we said beryllium follows the Duet rule when it makes ionic compounds, but defaults to the octet rule and becomes electron deficient when it makes covalent compounds. And you might think, what if one of these, let's just say for boron, let's say one of these lone pairs from fluorine pushes in, and you get a double bond. Okay, well then the fluorines would have an octet, and boron has an octet. Yeah, there's a problem with that. Boron's a small molecule. The energy shell it's in doesn't really allow too much for that, but more than anything, its behavior says, no, it's not really going to do that. So what do we mean by its behavior? Well, boron trifluoride is an example of a molecule that you find a lot in what we call coordinate covalent bonding. So coordinate covalent or dative bonding is a bond that's created where one species provides both of the electrons for the bond. And so let's look at what we have. Let's say we have ammonia. And we have our boron, trifluoride. What we find boron trifluoride does a lot is it then will coordinate covalent bond with the ammonia, where the ammonia provides both of the electrons for the bond, and we end up with a new compound. Let's do, so, yeah, we need the, okay, so because these boron compounds undergo coordinate covalent bonding quite a bit, if you had a double bond on one of the fluorines, this wouldn't be possible. And so there's one behavior. Also, in a little bit, probably tomorrow, you'll see what we call formal charges. Formal charges also prevent that that double bond from one of the fluorines. So boron is going to be pretty much a perpetually electron deficient atom. But some molecules have atoms that go beyond the octet rule in what's called an expanded valence. So, for example, let's look at phosphorus pentafluoride. Okay, so phosphorus is in the same group as nitrogen, so it has 5 valence. Fluorine, of course, has its 7. And then we say, well, for pentafluoride, I'm going to put phosphorus in the middle. And then, so basically, each one of these becomes a bonding location. And so then we start saying, well, and now you notice phosphorus has 10 electrons around it, 2 per bond. 5 bonds is 10 electrons. And you say, well, how can this happen? Well, we need to start thinking about the energy environment for larger atoms. So phosphorus, its electron structure will be 3s2, 3p3. So you notice that the valence has hit the n equals 3 level. So we know that our valence has 3s2, 3p3. However, n equals 3, what else exists that we're not showing here? You'll show it once you get to period 4 of the periodic table and you hit the transition metals, but at n equals 3 energetically, 3d also exists. It's slightly higher in energy than the 3p, but it's there, it's in the shell. It's just not filled. So it's energetically available. Now, those 10 electrons are not just going to fill into the D level. What's going to happen is something we call hybridization, which when I put up chapter 9, you'll see what this is. Uh, I'll be putting up chapter 9, it's tonight or tomorrow, but chapter 9 is going to finish off the rest of the summer. And so what's going to happen is this s orbital All three of these p orbitals and one of your d orbitals are going to be hybridized into, so that's 1, 2, 3, 4, 5 orbitals into 5 degenerate orbitals, so same energy, that are going to be the hybrid sp3d. And then, of course, you see the 4d orbitals that weren't used. Those are still just kind of left over out here in space. But then what happens, you say, well, my phosphorus has 5 electrons, 5 valence electrons. So it's going to go 1, 2, 3, 4, 5. And now it has 5 bonding locations where the fluorines can come in 1, 2, 3, 4, 5. And so now I have the ability to have that pentafluoride on there because of the energy environment of the phosphorus being a larger atom. Okay, so here we go. SF6, sulfur hexafluoride, which look up the YouTube videos of sulfur hexafluoride. Kind of fun. Uh, can be toxic, so don't play with it yourself. I'm not exactly sure where you get some, but still, you can look up the YouTube videos. Pretty fun. Then we have chlorine pentafluoride and xenon tetrafluoride. So here, xenon, you see, you have a noble gas that is forming bonds. So again, we have rules, but they're not absolute. They're Our rules are general that can help us explain most of what's going on, but there's always going to be exceptions. Ask anyone who's ever learned English as a second language. English has a list of rules, and then it has all the exceptions, which outweigh the rules. But let's work on these molecules. SF6, so sulfur, fluorine. Sulfur is in oxygen's group, so 1, 2, 3, 4, 5, 6. Fluorine 1, 2, 3, 4, 5, 6, 7. You notice that technically sulfur can have six bonding electrons, and fluorine has its one. So then we're going to get sulfur 2, 3, 4, 5, 6. And then since each fluorine used that location, sulfur did 1, 2, 3, 4, 5, 6. And again, later on, you'll see that that's due to hybridization. So now the fluorines, we need to replace the lone pairs. And you're also going to find very rarely do your halogens hybridize because they already have so many valence electrons. They can just rotate in space to make single bonds. Okay, but you notice that this sulfur has 1, 2, 3, 6 bonds, 2 apiece. It has 12 electrons around it. So this is expanded valence. What about ClF5? Well, this is a little different. So the chlorine, both the chlorine and the fluorine have 7 valence. This is one of the exceptions where chlorine is going to hybridize, and you're going to get fluorine in the 1, 2, 3, 4, 5. So let's see, fluorine, 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 fluorine. Now let's look at the chlorine. It has 5 bonds to it. So that means I used 1, 2, 3, 4, 5 of the electrons around it. You see that lone pair that's left over? Well, we have to put that back in there. We'll go ahead and replace the lone pairs around the fluorines. And then the chlorine has to have a leftover lone pair for itself. So that puts 12 around the chlorine. Okay, so then let's look at xenon F4. Okay, so xenon is a noble gas. So it has all eight of its valence electrons. Fluorine has seven valence, but I need to put four of these fluorines around the xenon, so let's do that. Going to replace the lone pairs on the fluorines that we didn't use. And then, well, how many of the electrons from xenon did I use? One, two, three, four, one per bond. And so that means xenon is going to have one, two, so two lone pairs left over. So these are going to be expanded valence molecules. Okay, so Lewis structures can be a little confusing when you first start, but really all they're going to take is practice, and you get used to how they go and what they're about. All right, so we will just continue on tomorrow as we finish out this last week of the summer session.